Okay, today is, I've been working on this for a little bit now, finally got it working. Turned out to be a simple bug, but um, previously I discussed how to do arbitrary um, Hamilton Hamiltonians in Circ. Now we're doing it in Tensorflow-Quantum, which is faster and more robust because a lot of the optimization techniques in Circ are either not robust to noise or my own implementations, which are obviously unoptimized. Um, and so we can see, we'll be able to see that TensorFlow-Quantum can do it a lot faster. It just took a little discussion with some of the devs for me to realize that there's a simple way to create a custom layer that will do everything we need. So once again, the goal of the variational quantum eigensolver is to find the ground state of, I should really define this ground state, because we know that the expectation value of this Hamiltonian is always greater than or equal to the lowest eigenvalue, or the ground state energy. And so a lot of times this will be for some sort of molecule or some sort of something that you like. Ground state energy is important in chemistry. In this case, I'm just doing random matrices. Like in theory, this is just any matrix that is easily decomposable into polysums. So that's why molecules are popular, is because they often have Hamiltonians that can be easily decomposed into polysums. So let's just get into the code here. There we go. So yeah, pretty standard imports. Just some additional tools for little hacks that I did. Oh, one thing I do want to say is when we're looking at the Handsats of this example, we have our circuit. So remember, the general stage is if we have our initial qubits here. The general stage is, oh wow, I cannot draw. We prepare this parametrized state, then we apply the Hamiltonian, and then we, let's see if I can draw the little measurement boxes like you see in quantum systems, and we approximate the Hamiltonian. And so for this part, we have, this is, let me double check, yeah, Rx, Rz. These are Rx, Rz, Rx, Rz, followed by C0 gates. And this all the way down, these go all the way down, and these go all the way down. And this is one layer, and so we can have however many layers. I think usually I have 2 layers standard in this code. And note that each one of these parameters, so there's 2 times qubits per layer. So the number of parameters is 2 times the number of qubits, because there's just 2 different parameters on every qubit. And so that's, I just want to draw that real quick before we go into the code, because we can see, that the each layer is this Rx, Rz on each of the qubits, followed by a C0 on each of them. And then we construct the parametrized ansatz by creating however many layers we need. And then we can scroll down first before we get into these other functions. actually, no, we'll get into them. So we'll look here and we can see that to create the VQE circuit, we create the Handsats as described, the circuit that's parametrized, and then we add the Hamiltonian. And this is really simple. In this case, all we have to do is rotate it so that we can measure the Z computational basis. So we can rotate for the X or we can rotate for the Y. Nothing to do if it's Z because it's just already in the Z basis. And so that's all we need to do to create the circuit. This is pretty simple. This is common code shared, I think, like among all of my VQE codes. And then we need that. And then we need one more thing, which is new, and this is prod. By the way, I did not write this. I should be forthcoming and say I just copied this code from Stack Overflow. But this is like, you know how sum is a built-in operation for lists? This is the same thing as sum, but for product. So it multiplies all the elements in a list instead of summing them. This actually exists in Python in 3.8, but I'm running 3.7.9 for keeping all my version control consistent with TensorFlow and TensorFlow-Quantum. Apparently Guido, or I can't remember, whatever the guy is who is like in charge of Python, the founder of Python, didn't believe it was necessary to have a product, and so they waited until 3.8 came out to add it to the math package. And so yeah, so this is within a single, this is the tensor product, right? Because we're measuring for, when we decompose the Hamiltonian, for a single Hamiltonian, we're measuring decomposed Hamiltonian. And so for a single tensor product of Pauli operators, we're measuring a single value. And so we multiply it. So we measure the Z basis, or we just take 1 if it's the identity. Remember, we don't measure, you can't measure the identity, it's just a 1, which actually does nothing, right? This is product, multiplying it by 1 does nothing. I could just drop it. I could just drop that actually. But I just like the placeholder. Actually, hold on. I realized I might actually slow down the code, so I changed that. So basically, we just measure all the Z outputs if they're not the identity. And this is pretty standard. This is different than previous TensorFlow-Quantum implementations because in the 1 qubit case, it's 1 qubit. We don't need to do any tensor product work. In the 2 qubit case, that's where I was having confusions. I don't know if you remember, but I was struggling with the conversion of the readouts to the unitary operators, and so like if you're reading out, and if you want to get one value, like this would be something you would do in penny lane, right? You could do in penny lane, you would do something like all Z of 0 and Z of 0 or of 1. So this might be something you would do in penny lane, right? But then you have to adjust for readout operators in this case because you're doing a tensor product readout operator. And so that was a whole thing I was struggling with, but then I realized that wasn't actually necessary. You could just do this simple. You could just multiply the Z readouts together. So then we have the Realmen Calculator. Just calculates the eigenvalues, the real eigenvalues, or the real minimum eigenvalue. So it just recreates the matrix from the inputs and then finds the eigenvalues using NumPy. So here we have some hyperparameters. This is the decomposition factor, how much you're breaking it down by. This is the number of qubits. I'll decrease that just for now. Then it just randomly creates them. The layers is this is how many layers in your quantum circuit you want to have. I just have 2 for now. We can see that this is the number of layers times 2q, and so that's the number of parameters. And so here is where what was stumping me for a while came in, right? So if we want to have multiple multiple circuits. But we want them to share parameters. That was something I was struggling with in Tensorflow-Quantum. However, the key was to actually make a VQE layer. So here we can see this is just one layer that manages all of them, because normally if you were to try and like what I try to do is create you could create multiple PQC layers or a single parameterized layer, and then use a TFQ.expectation or .sampled expectation or something. But the problem was, because the Keras layers are super helpful and nice and everything, they hide the variables from you. They don't, this is one of those things in Python where it's like, if you coming from C++ and now you're looking at Python and you're handling lists and you're confused about that, it's like, sometimes, for example, in Python, you can pass a function or a class a list, and it's essentially passing it by reference, which is, but it's hidden away, right? You don't have pointers or anything in Python, and so that can be confusing. But to deal with that, Keras just says we're copying everything by value. We're not looking at it as references. So if you pass us weight, a weight matrix, and then you change your weight matrix outside of the Keras layer, it doesn't change the Keras layer. And so creating shared weights is difficult. There are ways to do it in a Keras. You can alias the normally what you do in Keras if you want to share weights is you'd make one layer that you could then, if you did some, you could just make one layer, right? This, and then call it. You could, if you have, then you could do whatever you want. You could call it multiple times. This would work. The X would have one layers because one weight. The weight is associated with one instantiation of the layer. However, because the readout operators are different, you can't just make one layer and reference it constantly. And so that's where the challenge came in. So enough about the challenge. Let's get into the implementation. So we create a custom layer that takes in all of the circuits and operations. So this is really, a list of lists, where this is the breakdown of each circuit. And this is, so if we decompose the Hamiltonian into 5 circuits or 5 sub tensor products, this is going to be length 5. This is also going to be length 5 because this is the readout ops for each circuit. Really, this is actually the same pretty much for every case, but because the identity matrix is in there, that's why it's different. So this is just standard practice. You inherit from TensorFlow layers. You do super to initialize everything. And so these are the weights. And so we initialize them. I guess I should probably say, it doesn't matter. Normally you would label this with trainable equals true, but it doesn't really matter. And so we create random weights. Because of the way the controlled PQC works, they're supposed to be the shape 1, num weights. That's just a little fun fact. We do data type TensorFlow.float32, and then we have this. So this is the list of the sub breakdown of the Hamiltonian. So we create. If you're not familiar with the controlled PQC, it's like the same as the PQC, except the parameters are given by the user in some way, shape, or form. And so in this case, you can see when we call it, we're using our parameters. So this is just saying, don't worry about needing the parameters because the user is going to provide them to you. So we have circuits and ops for each of the decomposition terms, and then we have parameter shift rule differentiator, and we use 1,000 samples to estimate the expectation value. Then for the call, we sum over the output of each of these decompositions, and we called each layer on the input, which is just a blank circuit, right? Just this empty circuit, and the weights. So this is us providing the exact same values to every single parametrized circuit for all of the layers. And so we can see when we create it, first we want to create all the readout ops and all the circuits. So we just iterate through the Hamiltonian and create all of these. Then we instantiate it with the number of parameters, the circuits, and the operations. And then we just make a simple model because this, remember, it's going to output a single value, that's summation. And we can see it's going to have 12 trainable variables in this case, because it's 2 times 3 times 2, which is 12. And then we find the real min. We use add a grad, learning rate 0.2, as in the penny lane videos. And then we can take a step and do the typical gradient calculation. So this is just exactly, if you know TensorFlow, you've seen this before. Although there is no loss function, that might be different. We get the guess, and we just directly want to minimize that thing. So we don't use any loss function. That just is the loss. So we calculate the gradient, then we apply the gradient, and so you can see we don't even have to worry. Because of this custom layer, we can just handle it all within TensorFlow's built-in things. And then we append it so we can see the we can see what the value is at the end. And so then if we actually go and run this, we can see exactly what will happen is that we'll see at each epoch that this will print and it will be minimized. So if I go over, there we go. And so this is with a random. I missed it. This is with a random Hamiltonian. This is not any one of particular interest. It's not any molecule or anything like that. So we can let this execute, and you can see the minimization process going on right here as it gets very close to the actual minimum. And I'll show the graph too. Okay, there we go. So yeah, you can see the real min plotted here and the the guess as it decreases. Oh, I just noticed you can't see my cursor on it. That's unfortunate. And so yeah, that's the VQE of arbitrary Hamiltonian size in Tensorflow-Quantum. Just for an example, oh, that's messed up. Just for an example, we can do a 5-qubit Hamiltonian with the same decomposition value, which is a lot more complex as the Hamiltonian increases in size. It gets a lot more challenging because keep in mind let me handle that real quick. The problem was actually that problem only occurs when there's when you get an all identity matrix. So it tries to initialize a layer, but there's no readout ops, and so it gets mad, it errors out. And so if you notice, I can't scroll up anymore, but that's because the input was all, one of them was all identity was the identity matrix. And so that's what I was debugging with. If you do want if you want a constant, right, if you're trying to apply this to some real system, and a lot of real systems have that constant, what you can do is you can go to the show this. You can go down here and you could just add something. You could just add plus constant right here, and it'll minimize that function. Oh, right, I need to go back. So we can see now this one has 5 times 2 times 2, which is 20. You can see as it increases, right, it's getting a lot harder to minimize. It reaches a local minimum of negative 1.5 or so. So we can see that as the Hamiltonian increases in size, oh, that's not what I meant to do. I need to add a window capture. You can see it gets harder. Different optimizers might work. Rotosolve might come in here, but it's also worth noting that what I was going to say before it aired out is when I'm talking about qubits, right? I'm talking about exponential increases with one more qubit, right? It's an exponential, it's 5 qubits represents a 2 to the 5th matrix. So this is a 32 by 32 matrix, which would have, if they're all distinct eigenvalues, then it would have 32 eigenvalues. And it's worth noting that this matrix is not necessarily Hermitian, which means they're the same properties that are important for this system might not always work. So creating random matrices isn't always the best, because I'm not 100% sure that these created ones are always Hermitian, and there's certain properties. For example, the eigenvectors of Hermitian matrices are always orthogonal, which is and every quantum operator is a Hermitian matrix. And so I'm not sure if that has any impact on this, but that is worth noting. And so that's pretty much it. Because this is taking so long, I figure I will divvy it up, because I was going to include the subspace search variational quantum eigensolver, but I will separate that out because we're already at 22 minutes. And so, yeah, I'll also be discussing SSVQE, which is finding any arbitrary number of eigenvalues, not just the lowest one, next time.